Hello again, and welcome back. This is Joe Strout, and this is the live coding session making the Base Defender game, episode 4. In this episode, we're going to add turrets to the castle so it can defend itself, and then hopefully we'll have time to get started making a tile display and using that to control where the enemies and the player can go. So as always, let's start by checking out what we've got so far, making sure it actually runs. Main is the main program, so we'll just we'll do reset, run main. All right, and here we are. Got these little orange invading tanks, and I can damage them by either running into them or let my little auto tower here do the work for me. So very cool. But once they get to the castle, they just sit there and wail on the castle until I come over here and do something about it. The castle can't defend itself, even though it has these 4 little mini towers. So we're going to put turrets on those mini towers now. And that will be enough of that before we turn to navigation on the map. So right now, the castle is defined in the main program. Let's see, we have... that's weird. Huh. My navigation menu isn't detecting... well, the castle class doesn't actually have any methods. That's why. The castle is just a sprite, and I place it and I push it, and that's it. It's got no code at all yet. So this is going to have to go into a new module. Let's cut that. Save, reset, save as castle, this empty program, and then paste this in. Okay, so what's our castle going to need? It's going to need to import some stuff if we want to be able to test it on its own, which is always a good idea, I think. So let's import utils so that we can then ensure import resources. Since we're using resources castle image, sprite disp will just define in the main test program like we have in the other modules. So locals is equal to globals, then sprite disp equals display4, sprite disp clear, and if, and then what I did in the other modules is I made a setup method, which I think is a good idea. Yeah, here's what I'm going to do. All of this stuff I'm going to make part of a castle class, and then I'll instantiate the castle as an instance of that class. Is there any point in that? Actually, I'm not sure there's any point in that. There's only one castle. There's only ever going to be one castle. Nah, we don't need a class for it. So, by the way, if you hear pathetic noises from off screen, that's one of my cats. I've closed the office door and he's not happy about it. But if I don't, he'll be up here getting all up in my space and disrupting the recording. So sorry if you can hear that. He's fine. Trust me, he's totally fine. Okay, so we're going to have a castle class, but we're only going to do this in setup method. So setup equals function. All right, so now we can call castle.setup from the main program. But when we're testing, we'll just do setup. Let's try this much. Constants. Got to import that as well. Okay, cool. That adds our castle, but no turrets. Turrets are defined in tower. Yeah, I'm having a little regret about how I named that. Maybe I should have named it turret, but it's okay. Let's take a quick review of what's in there. There's a turret class. It's global. That's all we need to know, really. It has details that we don't care about at this point. So let's edit castle. Okay. There's going to be 4 of these, but you know what? Let's just start with 1. So let's ensure import tower, and then we'll have a turret class. So we can do t equals new turret, t dot position. No, that's not a thing. T dot x equals castle dot x. All right, how big is the castle? Nope, can't check that. What do you mean unknown? Oh, I didn't set up. Oh, because castle is now a local variable. Yeah, that's kind of a mistake. Let's do outer.castle. Okay, so now it'll be stored at the module level. From the main program, we can refer to it as castle.castle, and that's fine. But here, since I just ran it directly, we have a castle, and a castle image has a width and height of 192. You know what? This is an inefficient way to get this answer. I'm trying to figure out where the turrets are relative to the center of the castle. Let's just switch to our graphic. Yeah, that's how I make the little thumbnails for the videos, but that's not what we want now. We want buildings. Okay. And keeping in mind that all these are scaled down by half, but unscaled, it looks like the distance from the center to the turret is almost 72, but I'm not quite at the center of the turret, am I? It'd be halfway between 72 and 64, I think. Okay. Halfway between 72 and 64, which is, let's see, doing math, 69? 68, right, of course. They're all even numbers. Yeah, okay, so 68. All right. So castle x minus 68, t dot y equals castle dot y minus 68. And there was an init method, wasn't there? Yeah, there was, and it actually took x and y. Oh wait, no, that was on the tower. I don't think turrets need an init or have an init method. I think it's just like that. So we can do sprite sprites.push t, and that should get us a tower. Well, I missed because I forgot to take into account the scaling factor. So we'll include castle.scale in each of these. And yeah, oops. Save it, run it. Hey, there we go. Tower right on that, or sorry, a turret right on that tower. That looks nice. That's really cool. Actually, let's get all four of them now. So we want to loop for dx in -1, 1, for dy in -1, 1. Make a turret, and we'll multiply this offset by dx and dy. What do you mean end function? Whoa, oh boy, I've made a mess. And for that one, end function, this one. Okay, save it, run it. Cool, 4 turrets. Now, that might be all there is to it. Because turrets automatically know how to target the nearest enemy and shoot. The only other thing we want to do, though, is since they're smaller turrets, we're going to reduce the damage that they do. So we'll do t dot damage equals 2. I think the big turrets do 4. So half as much on these small ones. Now let's go to the main program. And where we used to, well, where we set up everything, we'll set up the castle. Which of course requires that we import castle. All right. Setup not found in map on line 42. That surprises me, because I'm sure we made a setup method. see if we're overwriting castle somewhere. Nope. All we're doing is importing it and calling setup. There's a setup function. What's the deal? Castle is a... let's pre-print that. Hey. That's not a module. That's some kind of sprite. Yeah. Why? Why is that? Right. Because I didn't reset. Okay. Now enemies.ms has a gripe on line 28. Which is where it's trying to target something. And its target doesn't have an X and a Y. Oh, right. I know what's going on here. Castle used to be a sprite. Now Castle is a module. And there are other bits of code that are assuming Castle is a global variable. And it is kind of convenient as a global variable. The problem is, well, you know what? Here's a trick. Oops. Did I make any changes to enemies? I did. I just fixed the formatting a little bit. Okay. It's quite possible as an import module to return something to use other than the module itself. So we could return castle. And that means this module returns castle as its value rather than the module itself. After importing it, you'll have castle as a direct reference to the castle. I'm apparently really bad at typing the word castle. Okay, so yeah, this is a sanctioned trick. If you have an import module that returns something, then that becomes the value instead of the module itself and all of the module methods. Oh, but then I can't do setup. Okay, it's going to have to auto setup, but it can't. Can it? It can as long as it's imported last. So we'll have it call setup and then return castle. Yeah. I think that'll work. Save it. Let's check main. As long as castle imported this last. And then we don't have to call castle setup anymore because castle is going to just be its own thing. Hey, it could work. No. What is castle now? Wait, I didn't reset. Okay, sprite disp is unknown. There's the problem. Import after sprite disp. Okay, I don't know if I love this. I might revisit this in a later session, but let's keep going with it. See how it works out. Hey, look at that! Nice. Oh, that's fun. I know. I feel like I hardly have to do anything as a player, and that's okay because this is in large part a tower defense game. It's just one where you get to, go out and get involved in the action when you need to. So that's cool. All right, our castle has towers, and our tower has towers, and those enemy tanks don't really stand a chance at this point. So that's cool. All right, I'm gonna move the tower back to the left because the castle doesn't need the help anymore. I mean, it does, but wow, look how short our main program has gotten. That's really cool. Yeah, we're gonna move this over to 300. Where's our castle? I think if I don't do reset run main, then you don't get a proper reset. All right, cool. It is time to make a map. This is going to be fun. All right, so we're going to use a tile display. Tile displays are certainly the most complicated kind of display in Mini Micro, so it wouldn't hurt to check the wiki. Because it takes some setup. You've got to define the tile set and how big the tiles are in that, and then you have to define how big you want them to be on the screen, whether you want any overlap, and so on. Now, I have been arguing with myself about whether to use a hexagonal map or a simple square map. And what I've decided to do is start with a simple square map, but keep all of the accesses to that tile display behind some functions that I put in a map module, so that if I later decide I want to switch to a hexagonal map, I just have to update the map module and hopefully don't have to touch the rest of the code. But for now, it's going to be a simple square tile display. So let's reset and start a map module. Oh wait, I can't call it map. Map is a built-in type in MiniScript. So what should we call it? Grid. Yeah, this will be the grid module. Okay. So let's import. I don't know what this thing's going to need to import. Probably constants at some point. But for now, we're going to just set up a tile display. So let's see. In the actual game, I don't even know if the tile display will need to be visible. Because what I'm thinking of using it for is mostly pathfinding. And during debugging, I'll want it visible so that I can see it. I can see how, you know, the data, the distance of each cell to the castle or to the nearest tower, that sort of thing. But during actual gameplay, it'll probably be an uninstalled display, just used for its convenience and storing easily visualizable data. So where to put it? That's the question. Right now we're using display 4 as the sprite display and display 5, the default graphics, as the graphics, the background, the faint blue grid. So where's this one go? Well, this, if we display it at all, we'll probably have it replacing the background. That makes sense. Okay. So for now, we're going to forget about the blue grid and just get our tile display up where we can work with it. So TD equals, let's see. I want a setup function. All right, display 5 equals, mode equals display mode tile. And then outer.td for tile display equals display 5. Okay, td.clear. All right, so what do we need here? We need the extent and the cell size, the size of the tiles on screen, and then extent is how many of them we have. So let's do some math. The screen is 960 by 640, and these grid lines are 64 apart. I think I want my display to be 32, to have 32 pixel cells. So if we do 960 over 32, that's 30 cells horizontally, oops, and 20 cells vertically, 30 by 20. T.extent equals 30, 20, T.cell size is 32. And then for initial testing purposes, let's just throw up a checkerboard pattern using the cell tint, using the set cell tint XY tint. So for x in range 0 to td.extent 0. You know what? This is an expression I'm going to be using a lot. Let's just stick it in the outer dot columns equals range from 0 to extent 0 minus 1. So that'd be 0 through 29 for the columns, and outer dot rows equals range 0 td dot extent 1 minus 1. So 0 to 19 for the rows. We can say for x in columns, for y in rows, td dot set cell tint x, y, and let's do a dark blue. If actually here we'll do it this way. Color.rgb 0 0 I don't know, 50 times x plus y mod 2. I think that'll get me a checkerboard. I'm just going to code experimentally today and see if that works. If locals equals globals, then setup. I'm going to clear before I do that. All right, run. Tile not found in map line 5. I don't think that's capitalized. Yeah, display modes are not capitalized. Run. Hey. I don't know if you can see that checkerboard. It's awfully faint. I'm going to make it a little bit easier to see. Let's put in a little red and green, and then make this 150. Yeah, there we go. Okay, cool. So we have a tile display. Now, we want to throw up some barriers. And I think here I want to load something that I can use at least to stand in graphics. So let's do our favorite trick, view find file, and let's look on the sys disk at what we've got here. Well, there's hex tiles. Tile shapes. This is the one. So using tile shapes, if we were to look at this one here, this is a rounded block. That's always good because it very clearly fills the tile, and yet because the little corners are rounded, you can easily count them, which is great for debugging. So what's the index of that? Index starts at 0, and oh, actually, once I assign it to the tile display, the view command in MiniMicro 1.2.1 will show us the indexes. So let's do that. And that was, let's get that path one more time. It's tile shapes. Yeah. Okay, let's copy this. Oops. And I'm not going to put this in resources because this is only temporary. This is for debugging. So we're just going to hard code this right in here. So let's see. td.tileset equals file load image. Maybe throw some quotation marks around that. How about, there we go. And then if I were to clear to, let's just do that much. Okay, so we have td. Let's view td.tileset. Okay, that did not work. That's so strange. I know this is the latest version of MiniMicro because we have the zoom in out feature, and yet it's not drawing. It's not drawing the tile indexes. Why is that? And what happened to our checkerboard? I have many questions. Okay. Maybe it's that we didn't set the tile size. So td.tileset tile size. I think those are 64. No, I'm still not seeing my checkerboard. Clear to null, or clear to 0. Okay, so that's that. Oh look, and now it's working. Okay, so it was a matter of setting the tile size, and then in order to get my tinting to appear, I had to actually assign it some shape for each cell. Okay, so these numbers are really tiny. You probably can't see this on video on the YouTube video, but they start at 0, they count across to 7, and this one that we were looking at before is 8. So if I were to clear it to 8, everything would have this sort of rounded shape to it. But actually clearing to 0, which is a solid square, is fine. And then where we want to put obstacles, we'll use tile index 8. So let's define that as a constant somewhere. I'm not going to put it in the constants file because, again, this is kind of private to the grid module. But we'll say, we'll call it wall. Wall index equals 8. Okay. So now let's make an add wall. How do I want to do this? I don't really want to re-implement the Bressenham algorithm right now. So I think I'm only going to have horizontal or vertical walls. And if that's the case, I can just make one add wall method and be a little careful about how I call it, and it should work fine. So we're going to go from x0, y0 to x1, y1. And we're going to do that by, we use math_util move towards. No, that doesn't work. We use signed. Okay. All right. So, while true, we want to do td.setCell x0, y0 wall index and td.setCell tint 0, y0, and we'll just give them a bright, slightly bluish color because we're going for sort of a Tron kind of thing here. So CC FF. I guess I could have used insert color, but that's fine. These are red, green, and blue HTML style colors. That should be fine. Okay, and then we're going to do x0 equals x0 plus sine of x1 minus x0. That'll move it towards x1. Same thing here. How about just plus equals? There you go. Y1 minus y0. Right, and if x0 equals x1 and y0 equals y1, then break. Okay. Move this up above our setup function. Doesn't really matter, but it just strikes me as neater. And now in setup, let's add some walls. So add wall. Let's see. I don't know. Let's have a wall coming down from the top. So 20, 19 to 20, 10. Save it, run it. Hey, that's a wall. Yeah, I'm kind of picturing the castle here, sort of hiding behind that wall. And then we'll have a wall that comes out like this and up so that the bad guys have to work their way around and through. It's a little bit long though. I shouldn't get too caught up in tweaking it, but all right, let's add a horizontal wall. Starting all the way over at 29 over on the right. And how far up from the bottom? 10, 8, something like that. How about 9? And then coming over to roughly mid-screen, which would be 15. Oops. I went way too high. This whole screen is only 20 rows high. So I wanted to go at like 4 or 5. Okay. This is a little too much of a bottleneck. I'm going to shorten this up. I meant to shorten it up before and I actually made it worse. There we go. I want this to come out a little further and then up. So go all the way up to 10, maybe 11. Yeah. And now that wall from 11.5 going up to 13.5. Nope, I'm sorry, 11.13. Okay, cool. 15. All right, cool, we have walls. Now let's get this into the main program. And they won't actually do anything yet, but we'll make sure that it all looks good. So save that, edit main. We'll ensure import grid. And then we'll be sure to call, instead of draw background, well, all right, in addition to draw background, because the grid won't always be visible, we'll do grid.setup. All right, cool, there it is. But as you can see, everything just totally ignores those obstacles. So, what's next? Okay. To edit grid, we need a function to tell when a cell is blocked. Let's look at what we can do with a bounding box. It's not called bounding box, it's called bounds. We can check overlaps and contains. And actually, you know what? I think there's another method that's not documented here. I noticed it the other day and put it on my mental to-do list. I should put it on my actual to-do list. Because if we look at player.bounds, local bounds, player.player.local bounds. Right, it's a bounds. If we look at bounds.indexes, it has this overlaps line segment method. So that's kind of cool. I'm going to have to document that. That might be a new thing in MiniMicro 1.2.1 that I've already forgotten I added. But anyway, I don't think that's what we need. What do we need? As, yeah, all of my sprites have a bounding box. It'd be nice to see if the bounding box hits anything on the grid. How are we going to do that? Alternatively, we could check whether a point hits anything on the grid. That's easy to do. That's just a little bit of math. You can get the corners of a bounding box. So we could check each of the corners. Or we could draw a line segment across the top and use overlaps line segment. Or we could make a bounds for the cell and do a bounds check. Ooh, I kind of like that. Yeah. Okay. But however we do it, we're going to have a function called overlaps wall function of a sprite. Okay. BB is the sprite that world bounds. So now we just need to know whether this bounding box BB overlaps the wall and overlaps any wall. If it does, well, then the sprite can deal with it as it deals with colliding with anything else by stopping and backing up a little bit. Okay, cool. So we need a map of bounding boxes for each of the walls. Wall, how about this? Cell bounds equals a map where the key is what do we want to use for keys here? Should I use just row and column? Or should I use some kind of integer index? We'll just use row column for now. Actually, column row, value bounds. Okay. Add cell bounds equals function, column row. I'm gonna leave myself lots of notes here so I don't forget what's going on. A map of bounding boxes. For walls, obstacle, cells. I still have to think about how I'm going to know which cell bounds to look up, but I think we can do that by just taking a little region around the sprite. I certainly don't want to check the whole map, because that would be slow. Okay. Okay, so cell bounds. Right, b equals new bounds, bb dot x equals column times, oh, I didn't keep, I've got magic numbers in my setup. Well, it's not that magic, TD cell size, I can use that. And actually we want column plus a half to get the center, bb dot y equals row plus a half, width equals cell size. Cell size. Cell size is not capitalized. What's the matter with you? Okay. And then cell bounds of column row equals BB. So whenever we add a wall, we'll also do add cell bounds for that wall. Okay. So now we should have a cell bounds map, and here we just need to know if it overlaps. You know what? Actually, sprite or point. If sprite or point is a sprite, then we'll do this, else we'll just check x and y. So if you pass in a point like the mouse or like a projectile, then we just want to check x and y, which is easy. So let's do that first. Let's see, column equals sprite or point dot x divided by t dot cell size, and we want floor that. Row equals floor of sprite or point dot y divided by the cell size, and then we can check cell equals t dot cell. Let's go back. I don't even need the bounds for this. Yeah, cell at XY. Because we know that it'll be using, the cell will be set to wall index if it's a wall. Well, in fact, let's just check that. Return c.cell at column row is equal wall idx. Okay, and while true, we're going to do a quick test here. Text.row equals 25, print, overlaps, wall, mouse, yield. Okay, cool. So this much is working. When I mouse over any cell, you can see the little number in the corner here changes from 0 to 1. That much we've got working. Okay, so that was the easy case. Easy case, check a point. Harder case, check a bounding box. Okay, so I'm going to do this same thing, but we're going to check several cells around the column and row given. So for C in range call -1 to call +1, for R in range row -1 to row +1. Let's see, wall BB equals cell bounds.get column row. The get method is not a built-in. That's something that comes from maputil, so ensure import maputil. And what get does is it returns the value for this key if it exists, otherwise it returns null or some other default you specify, but we'll just let it return null. If wall bb and wall bb.overlaps bb, then return true. Okay, and if none of those things happen for all 9 cells that we're checking, then return false. Okay, so that's an overlaps wall method. I don't have an easy way to just test that in the main program, so we're gonna, test it from down here from our local tests. So we'll just test it in the context of the main program. And let's test it with enemies first. Enemies have a check collisions thing. We'll also do if grid.overlaps wall, then hopefully it'll never be overlapping one from behind, because if it is, it's going to morph straight through. But let's see, right now we have a hit method that takes a sprite. I don't have a sprite here, I just know that it hit the wall, but we'll do the same kind of reaction. Well, you know what, let's put it in a method though, self.hitWall, which means this could be a one-liner. Sure, cut up a little bit. All right, enemy.hitWall equals function self.speed equals 0, self.move forward plus 3. Hey, it could work. Let's find out. No, it does not work. Grid.ms line 52. Line 52 is what? Oh. I didn't pass in the sprite in enemies. I'm like, hey grid, does it overlap wall? And it's like, does what overlap the wall? I mean, honestly, self is what I meant. Okay. Let's try that again. Sprite is unknown in grid.ms. All right. 52. Sprite point. Sprite point. A sprite point is a sprite. What? What? Sprite is unknown in the context. Oh, line 56. 56. Sprite or point. World bounds. All right, wouldn't be hard to make that method work if you passed in a bounds as well, but I don't anticipate the need for that. So, hey, look at that. They're stuck on the walls. Awesome. Okay. Now the player's not. Let's do that next. Player shouldn't be able to go through walls either. So we're going to have a similar modification to player. But hey, this is actually really cool. I'll just plow through some of these guys. Oh, but I can shove them right through the wall. And that's going to be hard to avoid, but we'll deal with that another day. Let's edit player. Okay, player update, check collisions. If grid.overlaps self, then self.hit wall, just like we did with the other one. Player.hit wall equals function self.speed 0. And I'm going to actually do the kickback, self.move forward -3, because that seems to be very effective. Yeah. As long as you're facing the wall, it keeps you from penetrating it. It's not going to keep me from backing through the wall. Oh, but I'm not sure that these guys actually can back up. No, the player can't back up. Overlap's not found in map. What? Player, line 44. If grid not overlaps self. Self wall. Overlaps wall. That's what it was called. Also, just for the sake of sort of consistency, code hygiene, I'm not sure. I'm going to import grid here. Not really necessary because the main program's already done it, but it makes me happy. It brings me joy. Okay, so can I go through the wall? No, I cannot. I can sit here and sort of bounce. I can try to go through it at an angle, but it's no good. I can't do it. So if I want to... Oh, what happened there? I backed through it. So unfortunately, we can't really keep these guys from backing through walls. But with the sprite, that's real hard to do. I think I managed it in a corner. Yeah. In a corner, you can do it. Put yourself in a corner and then diagonally go to the other corner and you can get yourself in the wall. And once you're in the wall, it's hard to stop. It's hard to force you out because we don't know which way to push you to get you out of the wall. We just know you're touching the wall. So that's going to be kind of a bigger can of worms that I will probably have to spend a whole hour on at some point, but not today. Today, I want to get these guys being a little bit less stupid and have them actually going towards the castle. Despite the obstacles, which means they need to work their way around like this and then come down here and up there. How are we going to do that? We're going to flood fill the grid with the distance to the castle. This is going to be fun. All right, edit grid. We're going to need a method for this because we'll have to pass in the castle position. So let's see. Prepare distance map. It's function goal position. All right. So the big idea here is we're going to set the cell tins of each cell according to how far it is from the goal. And we'll do that by preparing a work list. which I'll call to do, which is going to be a list of cell positions. Starting with the position of the goal, but this is going to be in rows and columns. So floor of goal post.x divided by t.cell size. This is going to be a little list, column row list, and floor of goal post.y divided by t.cell size. So we're going to push that. We're also going to start with cell tint. How do I want to? I don't really want to try and pull the distance out of the cell tint. So I feel like we need, you know what we need? I should have done this for cell bounds as well. We need a 2D array. List util. Yeah, that's way better. Rows equals 20, columns equals 30, list.init 2D, columns, rows. Okay. And so now we can actually index into it as just column row. All right. So I'm changing cell bounds to be this 2D list, and and then I'm going to do the same thing for distance, but I will also this is going to be way more efficient. Okay. But I'll also set the cell tint. So we need distance map as a thing. Well, we can just do that here. Distance outer.distMap equals list.init2D, columns, rows. I think it's 2D with a lowercase d. I'll find out if I'm wrong. Okay, so we're going to start with, I don't like this already. Goal row equals this. Goal column equals this. Okay, now we can push goal column, goal row. Okay. And I want a helper method. Let's see, set distance, this function, column, row, dist. And this is going to store in our dist map. Column, row equals dist, and it's also going to tint the cell. So 2d.set cell tint, column, row, RGB, and finally, what do we want this distance map to look like? We'll make it super bright. That doesn't make any sense. I was going to say super bright where the distance is 0 and then falling off. Yeah, we could do that. Actually, that makes sense. 255 minus distance. We can play with this later. 0, 0. All right. So when we have the goal row in position, we can set distance goal column, goal row 0, and then we have our to-do list, and then, yeah, we're going to do sort of a recursive algorithm, but implemented with our own to-do list, so it's not recursive. That's using iteration, and we can just say while to-do, post equals to do dot pull. And then for our, we'll do columns first. For column in post 0, oops, range of post 0 minus 1 to post 0 plus 1. That's a range of columns around this position. For row in range, post 0, 1 minus 1 to post 1 plus 1. Thank you, syntax highlighting. All right. If dist map column row is equal to null, let's make sure that our dist map is initialized to null. Then we should get the distance of this position. D equals dist map of post 0, post 1. This would be cleaner if we introduced some local variables, wouldn't it? X equals position 0, Y equals position 1, and then we can say XY here. And this could be X. Much better. This could be Y. All right. Then set distance of column row to distance plus 1. And push it onto our to-do list. To-do push column row. All right, that should do it. I think I can actually test this locally by just hitting run. Oh yeah, look at it, it's doing it. It's checking the mouse thing. But now we can say distance. What did I call it? Prepare distance map. Yeah, prepare distance map and give it an XY. We'll just give it the mouse. I can't remember if those were separate parameters. Here's a way to find out. Reference a function, goalposts, yeah, okay. So prepare distance map around the mouse. Okay, index error. Right, because we're not doing any bounds checking. That's a good point. You can't just go willy-nilly checking the distance map for things that may not be in bounds. Well, we'll just do a quick check here. If C less than 0 or, we can do it on each of these actually. C less than 0 or C greater than or equal to columns, then continue. And same here, if R less than 0 or R greater than or equal to rows, then continue. Save that. Oops. Run it. Problem on line 92. I said of instead of if. If. Interesting. Okay, let's do it from here again. Yeah. Trouble is, it all looks like the same color because this is just not that far a distance, I guess. Let's look at dist map of, wow, that's really hard to read. Orange on red, huh? Of 0, 0. It's a distance of 25. So we could easily multiply our distance by 10 and have a much more visible map. So again, distance map from the mouse. Okay, now what's going on? Let's check our cell tint. td.cell tint 0, 0. The red here is E6, which is, gosh, just not very much. Oh, I know why. Okay, let's save. Reset. Run. Grid. I think it's because the data was already there. Maybe? Let's find out. Yeah, there we go. Check that out. Except that we're not observing the walls. So that's raw distance if you just ignore the walls. Add wall, really need an isWall function. IsWall function, column, row, return t dot cell, column, row is equal to wall index. Okay. So here we can say if is wall, column, row, then continue. So you don't get to set any distance on the walls themselves. Or should we set the distance map to something infinitely large in that case, so that our little tanks don't try to move into the walls thinking, ooh, distance 0, there's my target. Yeah, we should probably do that. Set distance CR and then 9, else if the distance map is null, then we do the usual thing. Okay, cool, let's try that. Reset, run TD, no, run grid, okay, and map it from the mouse. Boom. Hey, check that out. That looks nice. I maybe need to reduce that factor of 10 a little bit just so that you can better see the gradient. But you can see that red gets brighter and brighter as you get closer to the goal, which was just the mouse position in this case. Love it. I am going to reduce how quickly that red falls off a little bit. We'll go 8. But now I think we're ready to go to the main program. And as part of our setup, we'll do grid.prepare distance map to castle. Save it, run it. Nice. Okay. So now all these tanks have to do to find their way to the castle is move towards the cell, which has the lowest distance from wherever they are. And that should work. Hopefully we can do this efficiently. Oh, I'm almost out of time too. But I really want to get this much to work today, so let's do it. Enemies update. Pick a target, chase the target. Yeah, that's not really how we want it to work anymore. I want to keep this around. Not currently in use, but maybe useful later. But what we want to do is walk the gradient of the grid. Let's make sure it knows about the grid. Okay. So how do we want to do this? We want to see what cell we're in and face the surrounding cell that is closest. It means that they're not going to move in very straight lines. They're going to kind of go a little jaggy, always walking either straights or diagonals. But I think that's okay. I think that'll be interesting. All right, so I need the grid to, I need some grid helper functions. So we have isWall. Let's also have grid.column function of x, or let's say xy. That's better because when we have a hexagonal grid, what column or row you're in might depend on your x and your y. So, and this way we can just pass in a sprite. or a mouse or whatever, and we'll get the column. So return xy.x for now, divided by the cell size, taking the floor of that. All right, and row equals function xy, return floor of xy.y, divided by cell size. All right, and then distance to goal is function of xy. Yeah, this will work. This will work just fine. Although, you know what would work better is if I didn't, because the xy is going to be a computed value in this case. So I'm going to take them as separate parameters. I know that seems a little inconsistent and messy. If I have regress later, I'll change it because it's code. It's easy. So in this case, what do we want to do? We want to compute the column and the row. I feel like I've written this code before. Not exactly, I haven't. But it's going to be a lot like this. All right, and let's do some bounds checking. If 0 is less than or equal to column, which is less than or equal to columns, I should say less than, and 0 is less than or equal to row, which is less than rows, then return distance map of column row. Otherwise, return some crazy big number. If you're outside the map, your distance is infinite, where infinite is defined as 9,999. Good enough for me. Okay, so I don't actually know if we need these column and rows. What we need is distance to goal. And we're going to check a set of points around each enemy and have it face whichever one is closest. That should work. All right, so for P in no check points around check nearby points face closest. Okay, so for X in X self.x minus, oh, how do I undo this? Dx in negative, let's see, how big are these guys? They're about 30, 32, maybe 40 pixels in size, which means half their size is about 20. So we'll go minus 20, 0, 20 for dy in minus 20, 0, 20. If not dx and not dy, then continue. Otherwise, let's see. Best dist equals 9. Best facing, or best delta equals null. Okay. Dist equals grid dot distance to goal of self.x plus dx, self.y plus dy. If dist is, if dist is less than best dist, then best dist equals dist, best delta equals dx, dy. All right, and after all that, we just want to face in the direction of dx, dy. We don't have a handy function for that, but we can just do the math now. Hey, that's what algebra is for. So self.rotation equals arctangent of dy dx times 180 degrees per pi radians. Let's try it. Reset, run main. Okay, rows unknown, grid 48. Oh yeah. I bet you all saw that when I was typing it, didn't you? You were probably shouting at the screen. It's not all caps, it's lowercase. Oh well, the computer told me. Distance map is unknown. All right, what did we call it? Dist map. Okay. Uh-huh. Well, that's not good. Why are they not at least facing down the gradient? I mean, I get that I didn't set their speed, so they're not moving, but they should still be facing down the gradient. For these guys, I kind of believe it. This might be the best way to go, but for these guys, they should be facing this way. So something's very funny there. Let's get an enemy. Equals enemy dot enemies 0. Oh, good. E dot x is 800 and some. So it's one of these guys over here. E dot update. Well, here, let's start with rotation equals minus 90. Cool. It was this guy. He faces straight down. E dot update makes him face that way. I don't like that. That's not correct. Let's look for an obvious bug. Distance is -20 to 20, dy -20 to 20. Distance to goal, self.x plus dx and self.y plus dy. If it's better than the best distance, let's let's what? How are we going to get to the bottom of this? I'm thinking we have it print stuff. Distance is less than best distance. Yeah, of course you have to do that before we've lost it. And paste that all in. And now do an e dot update again. Oh boy. So 38 is less than 999 and distance minus 20 minus 20. Okay, sure. But those are both negative. It doesn't look to me like that's the way it's facing, so something's wrong with my A10. -20, -20. -2.35. And if we take that times 180 over pi, we get minus 135. Yeah, but it doesn't look to me like he's facing minus 135. E dot rotation, 45. Why is it 45? When I just did the math and it comes out to minus 135. I'm doing something silly. Oh, yeah, I know what I'm doing. You probably all saw this too. I'm using the last dx and dy rather than the best dx and dy, the best delta. Although it's a little funny that that came out with the negatives. I would have expected the last ones to be 20, 20. Oh, which it was. That's why it was facing 45 degrees. Okay. Best delta 0, actually 1. Best delta 0. Because for mathy reasons, a10 takes the y before the x. All right, cool. Let's take out the print, so that's going to be very printy. Reset, run main. Hey, cool. Look, they're all facing in a direction which takes them, I think, towards the castle. So, edit enemies. We just have to get their motors running. Let's see. Chase target. Did this. Oh, I actually like that the rotation moves smoothly as well. So let's do this. Target angle. Instead of saying the rotation directly, we're going to set target angle as that. Then we can rotate towards that angle and move towards it with some speed. This is going to be so cool. Not so cool. Okay, well, they all rotated in a sensible direction, but they're not moving. Right, because there was more to, oops, more to it. Self.speed equals that. Then we have to do this. Move forward and check collisions. And you know what? This comment here really doesn't say anything that the method name doesn't say, so let's get it out of there. Okay, speed. Move forward and check collisions. Okay. Now cool? Yes, now cool. Uh-oh. Except one of them wandered right off the screen and caused a bug in line 35. Line 35. Best delta. Oh, if the best delta is none, then what? I don't know. Why would that be? If it's wandered completely off the screen, then it's never going to find a distance to the goal that is less than 999, and so it's always going to be null. Yeah, that shouldn't really happen, but when it does happen, we're just going to destroy the tank. Yeah. Okay. Okay, not as smart as I was hoping. Follow the gradient. Why are they having so much trouble following that gradient? Okay, shoot, I'm really out of time. I don't like these videos to go much longer than an hour, plus I have something else I should be doing right now, but before I give it up, I'm going to add a little debug function. Let's see, text dot row equals 25, print grid dot distance to goal of the mouse with some spaces. That's weird. Why is it not updating? And also, where's my castle? Oh, let's try reset. Yeah, it's still strange that it's not updating. save that distance to goal of mouse, 28. Okay, well if the distance is always 28, then this is not going to work. So, where's our distance to goal method? Function, oh, it takes X and Y. Okay, sure, that's true. Mouse.x, mouse.y. Save that. Let's double check enemies. Make sure that we're passing in X and Y. Yes, we are. X and Y. Okay. Reset run main. Okay. So here's a problem. Down here, the goal is, it doesn't change very fast. So you could be following this gradient. Although, I mean, sure, it's always 27 all the way along here, but if you were to look up here, you'd see 26. So I think the problem is just that they're not looking far enough. They could be down here, and 20 pixels might be within the same cell. So let's edit enemies and have them look more like 30 pixels in each direction. And yeah, we could add more intermediate points, but let's see if we get by with this. Hey, there we go. Oh, they're getting stuck on the wall. Why would you get stuck on the wall? This is 15. This is 14. Oh, but that's 13. So it's trying to go past the corner and they can't quite make it. It's because they're trying to take diagonals. If we didn't have them take diagonals, then this would work. If we only check the 4 neighboring directions, but then their movement would be very unnatural. It would be very always going in straight lines kind of thing instead of following diagonals. So this will need some tweaking, but still I'm pretty pleased with this for a day's work. Next time we will refine that a little bit so that they don't get stuck up on corners like this. And well, that might actually be all we get done next time. I don't know, we'll see. We'll take it from there. So tune in next time, see how it goes. If you have any questions, leave them in the comments. And please visit our Discord. We'd love to hear from you. Until next time, happy coding.